Imagine you're trying to bake a world-class, award-winning cake,
Ooh,
right?
okay.
But your supplier just secretly changes the chemical makeup of your flour every single week,
Yeah, that would be a nightmare.
right? You would never stand for it. I mean, your recipes would fail, your customers complain, and the business tanks. But if you are a beverage engineer or a water treatment technician working right here in South Africa, that is exactly what you are dealing with when you hook up a brewery or, a bottling plant to a municipal tap.
Oh, absolutely. The water chemistry is just constantly shifting.
Exactly. You might have a beer recipe that tasted absolutely flawless in May, and then by September, that exact same recipe has drifted into something totally unrecognizable.
And the malt is identical, the hops are the same?
The yeast strain hasn't changed, but the source water chemistry has fundamentally altered the product.
Which, really forces a complete paradigm shift for the technicians who are sizing and installing this equipment. Because in most industrial settings, water is just treated like a basic utility. You just need it to run the boilers, cool the machinery, maybe wash down the facility floor.
Sure, you only care that it's relatively clean and safe.
Exactly. But when you step onto the floor of a beverage plant, the water isn't just supporting the product, it literally is the product.
It is the product, yeah.
So you are no longer answering the simple engineering question of, is this water safe to drink? You have to answer a vastly more difficult, commercially critical question for your client.
Which
Is this water mathematically identical to the water we used for the last batch?
and that is a massive challenge because municipal water, while staying perfectly legal and safe within its defined drinking parameters, it fluctuates wildly in its actual mineral makeup.
Oh, massively. Legal drinking water is simply not the same thing as a consistent, engineered, raw ingredient.
Right, so that is our mission for this deep dive. We are exploring the highly specific, zero-tolerance engineering challenges of brewing and beverage water.
It's a great topic.
And we are pulling our insights today entirely from an incredibly practical article living in the knowledge base on the DWT website.
Joe, it's a brilliant resource.
It really is. It's titled Brewing and Beverage Water, Alkalinity, Chlorophenols, and the RO and Rebuild Approach. And I want to jump straight into the chemistry of it all with you.
Let's do it.
So if the municipal water is constantly fluctuating, what specific chemical variables are actually ruining these recipes for your clients?
Look, it basically boils down to the biggest invisible battle happening in the brew house. And that battle is entirely about residual alkalinity.
Okay.
If we look at the modern standard reference for brewing water, specifically the work by Palmer and Kaminsky, they frame this entire chemical process as a microscopic tug of war happening inside the mash tun.
And just for clarity, the mash tun being the vessel where the brewers steep the crushed malt in hot water to extract the sugars.
Right, exactly. The enzymes in that mash, specifically the ones that convert the complex grain starches into the fermentable sugars that the yeast will eventually eat, they're incredibly temperamental.
Okay, how so?
They demand a highly specific, slightly acidic environment to function properly. The ultimate engineering target for that mash is to land perfectly at a pH of 5.2 to 5.6.
Wow, that is a really tight window.
It is.
And I imagine if you miss that narrow window, you're leaving unextracted sugars behind, hurting your yield, or worse, you start extracting harsh, astringent tannins from the grain husks.
Jay, it makes the beer taste like you're chewing on an old tea bag.
Ugh, terrible. So how does the water chemistry actually control that pH then?
Well, this is where Palmer and Kaminsky's tug-of-war analogy perfectly illustrates the mechanics. On one side of the rope, you have the alkalinity of the feed water,
Okay.
which acts as a buffer and actively pushes the pH of the mashup.
Right.
And then on the other side of the rope, you have minerals like calcium and magnesium, which react with the phosphates in the malt to pull the pH down. So it's this active shifting balance.
Which means standardizing the water treatment equipment for a client is, incredibly tricky because the target numbers change depending on the recipe they're brewing that day.
Exactly.
So let's talk about pale beers first. Your light lagers, your crisp pale ales. What are the actual numbers an engineer needs to hit to win this tug of war?
So pale beers demand very low residual alkalinity. And that's because the lightly kilned pale malts don't really contribute much acid of their own to help pull the pH down.
Ah, I see.
So the published guiding states that alkalinity needs to be maintained below roughly 50 milligrams per liter as calcium carbonate.
50, okay.
Share it out. And if your client is brewing the palest, most delicate styles, you actually need to push your treatment system harder to get that number closer to 25 milligrams per liter as calcium carbonate.
Wow, that's really low. But if that same client switches over to brewing a heavy, dark beer like a stout or a porter, the entire dynamic flips, right?
Completely flips. Jaron dark roasted malts, because of the heavy roasting process, they are highly acidic on their own.
Right.
So if you feed that mash tun the same near zero alkalinity water you used for the pale ale, the acidic malt will just drag the pH way down, well below that 5.2 floor.
Oh, and you end up with a beer that tastes thin, sharp, and intensely sour.
Exactly. You actually need high alkalinity in the water to act as a buffer against all that acidic roasted grain.
Which, is a brilliant mechanism that explains so much of brewing history.
Oh, it really does.
Long before reverse osmosis existed, geography strictly dictated the style of beer a region could successfully produce.
Right. The brewers simply adapted their recipes to survive whatever their local water chemistry was doing.
Yeah, that blew my mind when I made that connection reading the DWT article. It is literally the reason why a city like Pilsen, which sits on water with naturally near zero alkalinity, historically perfected the crisp, pale Pilsner.
Yeah.
The water just naturally nailed that 5.2 to 5.6 pH window for pale malts. Meanwhile, over in Dublin, the local water has incredibly high natural alkalinity.
Massive alkalinity there. Yeah.
If they tried to brew a Pilsner, it would have been a total disaster. But it was the absolute perfect buffering environment for brewing a dark, heavy stout.
It's fascinating. Geography used to be the ultimate brewmaster, but modern commercial brewing doesn't have the luxury of just shrugging and saying, oh, well, the water was different today, so the beer is a different color.
Right. A major brand requires absolute control over that pH tug of war to maintain global consistency.
Absolutely.
Okay, so say you engineer the perfect system. You balance the calcium and the alkalinity. You hit a gorgeous pH of 5.4. The starches convert beautifully. But then you taste the final beer, and it tastes like a hospital waiting room.
Oh, no.
It smells like a plastic bandage. Hitting the pH means absolutely nothing if you fail the next massive hurdle, which is the absolute non-negotiable requirement for any water treatment technician: complete dechlorination.
This is undoubtedly where the most catastrophic batch-ruining mistakes happen in water treatment design. I mean, a minor oversight here destroys the entire product.
Hectic.
We are talking about the formation of chlorophenols.
Let's break down the chemistry of that taint. The term in the article is wort phenolics. For the uninitiated, wort is just the unfermented beer, the sweet malt tea before the yeast gets to it.
Right.
And phenolics are natural organic compounds derived from the plant matter, like the malt and the hops.
Yeah.
So why is chlorine coming into contact with those phenolics such a disaster?
Because the reaction is instantaneous and it's highly aggressive. When chlorine or chloramine in the municipal feed water meets those natural wort phenolics, they bind together to create chlorophenols.
And that's the plastic taste.
Exactly. The result is that medicinal plastic, plaster-like taint you mentioned. And what makes this uniquely terrifying for a commercial brewer is the sensitivity of the human palate.
How sensitive are we talking?
Well, our evolutionary biology makes us hypersensitive to these specific compounds. The flavor threshold for detecting chlorophenols is in the low parts per billion.
Parts per billion. Let that sink in for you guys listening. That is virtually microscopic.
Yeah, it's nothing.
You could have an Olympic-sized swimming pool of beer, and a few drops of this compound would ruin the entire thing.
And once those chlorophenols are formed in the brew house, the battle is over.
It's done.
They are in the beer forever, Joe. You cannot fix it downstream. The vigorous boiling of the wort won't drive it off, the fermentation process won't mask it, and running the final beer through a filter won't catch it.
Wow.
The chlorine or chloramine must be completely eliminated from the feed water before it ever reaches the mash tun.
So let me put myself in the shoes of a practical technician working on the ground here. Most technicians learn their trade dealing with standard municipal chlorine, right?
Sure.
Let's say I've got a new brewery client in Gauteng. I look at my equipment list. I grab a standard activated carbon filter, the exact same kind I successfully use everywhere else for removing free chlorine, and I install it. Am I safe?
No, you are walking right into a trap that catches a lot of experienced people out.
Okay, why?
The Geographical reality for engineers working in Gauteng is that Rand Water applies chloramination as its secondary disinfection at its booster stations.
Okay, so they're treating the water with chloramine, not just free chlorine.
Exactly. And the distinction between those two chemicals completely changes the engineering of the filter.
Drastically, I imagine.
Drastically. Municipalities use chloramine specifically because it is highly stable. I mean, it is designed to survive for a very long time in the vast pipe network without breaking down.
Right, which is great for safe drinking water, but terrible for a brewer.
Exactly. So if you run that water through a standard carbon vessel that was sized merely for free chlorine, the chloramine will survive the journey. It will pass straight through the carbon bed and right into the brewery.
Ouch.
Breaking the chemical bond of chloramine requires a significantly longer contact time.
Meaning the water physically needs to spend more time touching the carbon inside the vessel?
Yes. The engineering metric is called empty bed contact time. The practical, non-negotiable answer for working in Gauteng is that you must use catalytic carbon, which is vastly more reactive.
Okay, catalytic carbon.
And your filter vessel must be specifically sized to provide that extended contact time. If you just throw a standard off-the-shelf chlorine filter at a chloramine problem, you are going to ruin the client's beer.
And they will be dumping thousands of liters down the drain.
Oh, absolutely. It's a massive financial loss.
This paints a pretty chaotic picture for an engineer. I mean, we have a wildly fluctuating municipal supply. We have a delicate razor-thin pH tug-of-war with alkalinity that changes based on the malt recipe. And we have an absolute zero-tolerance mandate for chloramine removal.
It's hectic.
If you are trying to help a commercial brewer achieve a consistent, style-accurate product nationwide, how do you actually juggle all that? You can't just stand there dosing tiny bits of acid and tweaking valves every morning based on whatever water happens to come out of the tap that day.
You don't even try.
You don't.
No. The modern gold standard practice in commercial beverage production is to simply stop fighting the municipality altogether. You don't tweak the water, you start from scratch. This is the RO and rebuild approach.
RO meaning reverse osmosis.
Yes.
So it's like you wipe the chalkboard completely clean before you draw your map, rather than trying to carefully erase around all the municipal scribbles.
That is the perfect visualization, yeah. It is a deliberate two-step philosophy. In step one, you push the municipal feed water through a reverse osmosis membrane.
Okay.
This physically strips the water down to a highly consistent, ultra-low mineral baseline. You rip out the alkalinity, you rip out the hardness, you remove all the environmental variables. You are literally left with a blank canvas.
And then comes step two, the rebuild.
Exactly. You selectively dose specific minerals back into that blank canvas, usually calcium sulfate or calcium chloride, in precise mathematical quantities.
Just to hit the exact target profile for the specific style you are brewing.
And this is where you, as the engineer, deliver massive commercial value to your client. I mean, yes, installing, powering, and maintaining a commercial reverse osmosis skid requires significantly more capital than just, dosing a little phosphoric acid into municipal tap water.
Sure, it's a big upfront cost.
But look at what that capital buys the brand. It makes their recipe completely portable and flawlessly repeatable.
The water becomes mathematically identical. It doesn't matter if it's the middle of a drought in February or a flood in August.
Exactly.
It doesn't matter if the franchise plant is located in Cape Town or Durban or up in Poliquin.
The RO and rebuild approach turns water from an unpredictable environmental liability into a fully controllable, engineered raw ingredient.
That's incredible.
You can digitally construct the exact mineral profile of historical Pilsen or historical Dublin on demand at the push of a button anywhere in the country.
Okay, so you've built the perfect digital water profile for a brewery. But the DWT article goes much further than beer. It dives into carbonated beverages, post-mix fountain installations, and bottled water.
It does, yeah.
And I have to assume that if you were dealing with a global giant like Coca-Cola, they don't leave anything to chance. They must put an absolute legal straitjacket on what a fast food franchise can run through their fountain systems.
Oh, it is a completely different regulatory and corporate landscape. In the food service and post-mix world, you aren't designing water to optimize enzyme extraction in a mash tun.
Right.
You are designing water to protect the highly engineered syrup and to stabilize the carbonation. Let's look at the actual numbers. Coca-Cola's food service water specification for post-mix installations is incredibly strict.
Let's hear the gauntlet an engineer has to run on one of these sites.
Okay, so the published spec requires absolute zero coliforms in 100 milliliters.
Zero. Okay, making sense.
Turbidity must be capped at or below 0.5 NTU.
Right.
Total chlorine has to be strictly at or below 0.5 milligrams per liter.
Okay, very low.
Total alkalinity must be held at or below 150 milligrams per liter. Hardness is capped at 100 milligrams per liter. And total dissolved solids, or TDS, must be at or below 500 milligrams per liter.
That is a serious list. Let me pause on a couple of those terms just to be crystal clear for everyone.
Okay.
Coliforms. We are talking about bacterial contamination, indicating the water is fundamentally unsanitary.
Correct. Zero tolerance there.
An NTU nephelometric turbidity units that measures cloudiness, right?
Correct. It measures the scattering of light by suspended particles.
Yeah.
So a limit of 0.5 NTU means that water must be microscopically, brilliantly clear.
And why is that clarity so vital for a fountain machine?
Because any suspended particulate will act as a nucleation point for carbon dioxide, which basically causes the beverage to wildly foam out of the cup instead of holding its fizz.
Nobody wants a flat, foamy Coke. And what about that alkalinity cap? Why does Coca-Cola care so deeply about keeping alkalinity below 150 milligrams per liter?
Because high alkalinity literally acts as an antacid.
Really?
The beverage syrup relies on a very specific dose of phosphoric acid or citric acid to give the soda its sharp, crisp bite. If the water has high alkalinity, it chemically neutralizes those syrup acids. Suddenly, your perfectly formulated soda tastes flat, soapy, and just entirely wrong. The water chemistry is actively fighting the syrup chemistry.
So how does a technician actually achieve all these strict metrics on site at a busy restaurant or a fast food outlet where they definitely don't have the space for a massive industrial RO plant?
Well, in the post-mix scenario, it is achieved through specialized NSFA NSI 42 certified filtration systems. And crucially, tying back to our earlier point about Gauteng, the certification must explicitly demonstrate chloramine reduction capabilities.
You can't just guess.
No, you cannot just guess that a filter works based on its physical size. The brand requires certified proof that the equipment meets those exact reduction parameters.
But when we scale up from a restaurant fountain to an actual large-scale bottling plant, the rules get even tighter.
Much tighter. Because a bottled beverage has to survive on a warehouse shelf for months without degrading.
Right. Shelf life is everything.
Bottling plant internal standards demand incredibly low alkalinity to protect flavor stability over the product's entire shelf life. This is why commercial bottling water treatment is almost universally membrane-based.
So they're using the RO and rebuild approach too.
Exactly. They rely on heavy reverse osmosis systems followed by micro-precise remineralization to ensure the water is utterly flawless before it ever touches the syrup.
Which brings us to the final and frankly most dangerous aspect of this whole process.
The legal side.
Exactly. You engineer the perfect water. It tastes identical to Dublin. The pH is flawless. The turbidity is zero. But the second your client takes that engineered water and seals it inside a plastic bottle to sell to the public, the engineering stops and the lawyers take over.
They absolutely do.
Let's pivot to the legal reality in South Africa.
Yeah.
Regulation R718 of 2006.
If an engineer's equipment design is going to be used to bottle water, understanding Regulation R718 is just as vital as understanding the RO membrane itself.
It's that serious.
Under South African law, bottled water is a highly defined, distinct legal category. You can't just put tap water in a plastic bottle, slap a picture of a mountain on it, and sell it.
The regulation rigidly splits the market, right? You have your natural waters, your waters defined by origin, and then you have this massive catch-all category called prepared waters.
And prepared water is the legal bucket that almost all commercial treatment plants fall into.
Okay.
By legal definition, it is water from any supply, including a municipal tap that has undergone acceptable physical or chemical treatment to make it ready for packaging.
The labeling rules in that regulation are what really caught my attention. They are incredibly specific, and an engineer absolutely needs to know these rules before they finalize a multi-million rand system design.
Definitely.
Because the equipment you choose literally dictates the client's marketing.
The law leaves absolutely no room for ambiguity. If a client treats municipal tap water using the equipment you installed, the label on the bottle must explicitly call the product prepared water.
No exceptions.
None. Furthermore, it must state the actual treatment method used. The regulation's own examples specify that terms like reverse osmosis or ozonated must be clearly printed.
So the client's marketing team can't just call it pure glacier spring water just because your RO skid made it perfectly clean.
Absolutely not. Natural mineral waters and spring waters have entirely different, incredibly strict composition requirements, and legally, they cannot be bulk transported from their source before bottling.
Wow, okay.
If your equipment is treating municipal tap water, the law dictates that the label must also carry the exact phrase from a public or private distribution system.
That is a critical warning for any technician or engineer. I mean, you do not want to design and commission a beautiful high-tech treatment plant only to have the client's entire product recalled because their marketing team printed an illegal label based on a misunderstanding of what your equipment actually does.
The legal liability is real, Ja.
Mm.
And compliance for bottled water goes far beyond just meeting SANS 241, which is the basic national standard for safe drinking water. Regulation R718 points directly to two other standards, SANS 1857 and SANS 1862, which police the specific testing methods and the hyper-strict contaminant limits required specifically for bottled water.
So safe drinking water is just the starting line. Bottled water is an entirely different race.
Exactly.
Man, we have covered a tremendous amount of ground today, moving from the microscopic chemistry of a mash tun to the legal wording on a plastic bottle. Let's summarize the core takeaways from the DWT website's knowledge base for the engineers and technicians listening.
Great idea.
If you are designing a system for brewing water, you must watch two things like a hawk. First, residual alkalinity, because that dictates your delicate pH tug-of-war. Second, chlorine or chloramine, which must be totally eradicated before the brew house to prevent that disastrous chlorophenols taint. And never forget the goetang trap. Chloramine demands catalytic carbon and extended empty bed contact times.
And if you're transitioning into bottling or post-mix installations, the rules shift. You must work directly from the published legal specifications of the brand you supply. Hit those NTU, TDS, and alkalinity limits with absolute precision to protect the syrup. And if you are setting up a commercial bottled water plant, read Regulation R718 before the client even registers a trademark.
Because the specific physical treatment equipment you select will legally mandate the words printed on the final label.
Absolutely.
It all comes back to that initial paradigm shift.
Yeah.
In this industry, the water isn't just a utility, it is the product.
Yeah.
Which leaves me with a lingering, somewhat philosophical question to mull over.
Okay, let's hear it.
We spent a lot of time talking about the power of the RO and rebuild concept.
Yeah.
If reverse osmosis allows an engineer to strip local municipal water down to absolute zero and then mathematically rebuild it to exactly match the historic water chemistry of Dublin or Pilsen or anywhere else,
Yeah.
does the concept of a true local beverage style even exist anymore? I mean, is geography now just a digital recipe file you download directly to your RO skid?
That's a profound way to look at it.
It makes you realize that modern water engineering hasn't just solved the consistency problem for these plants. It has entirely decoupled food and beverage manufacturing from geography. You don't ever have to worry about the supplier secretly changing the flour on you because you've figured out how to manufacture the absolute perfect flour from scratch, molecule by molecule, no matter where you are in the world.
A perfect blank canvas every single batch.
Exactly. Thanks for joining us on this deep dive. We'll catch you next time.